Hello everyone, this is topic 7 for exam 2, continuation of integration by parts, and this is what I refer to as either repeated applications and the tabular method. So we may require repeated applications of the integration by parts formula. So recall that when we realize that we need to use integration by parts, basically in this case it's because if we were to try to fit the basic form for, I'll just argue this on a piece of scrap paper, if we were to try to fit the basic form for the sine of u, then our choice of u would be 2x, and the du is just 2 dx. We can modify by the 2. Problem is we have this extra x squared. So therefore we need to use integration by parts because it's a product of two basic functions that does not fit a basic integration formula. And so we start by classifying the factors. X squared is considered to be algebraic. Sine of 2x, trigonometric. And we choose our u according to lie 8. So when we look at the algebraic and trigonometric, it tells us to choose the algebraic to be our u. So off to the side, our structure of the solution, pick our u, that's going to be x squared. In the du directly underneath, in another column a little bit off to the right, dv, which is the leftovers, sine of 2x dx, and then v is going to be directly underneath. So our du is calculated, that's 2x dx, and we don't modify by the constant there because recall that the integration by parts formula is the integral of u dv is equal to u times v minus the integral of v du, and it's identically du, okay? It's not a modified du. So then we integrate dv to get v. That's our integration formula for the sine of kx again, so recall that, it's negative 1 over k cosine of kx. We had that from last time. And so integrating sine of 2x, we get negative 1/2 cosine 2x. Okay, remember we don't add a constant of integration there. And we apply the integration by parts formula. The diagonal gives us u times v, and then minus the integral of the product of the horizontal gives us minus the integral of v du. And so we have u, which is x squared times v, negative 1/2 cosine 2x, and then minus the integral of v, negative 1/2 cosine 2x, times our du, which was 2x dx. And at that point, we'll clean things up. We'll rewrite this first term as negative 1/2 x squared cosine 2x. Okay, from the new integral, we can factor out this negative 1/2 and also the 2. So we're really factoring in negative 1 times this negative makes positive. And then the integral of, okay, instead of cosine 2x times x, those are the leftover factors, we prefer x cosine 2x and the differential dx. Now take a look at what happened here. That is, what was bothering us to begin with in the original integral was an x squared. And after one application of integration by parts, that factor of x was depressed to x to the first. And so therefore, if we use integration by parts again, if you look back at the last lecture, this is a situation that we saw where it requires a single application of integration by parts. So now if we do integration by parts another time, this x is going to vanish. And you could be consistent with the classification and our choice of u, according to Lie 8, would again be the algebraic x. dv now is cosine 2x, and the differential dx always associated with that. Our du is now 1 dx, and our v integrating cosine. So again, that's the cosine of kx formula. I'll just flash it real quick. There it is again. 1 over 2 times the sine of 2x. And then our u times v minus the integral of v du, our integration by parts formula, gives us, okay, the first term, this minus 1/2 x squared cosine 2x, we're done with that. That's part of the solution. But then we have plus, and our u times v is x and 1/2 sine of 2x, and then minus the integral of v, the 1/2 sine of 2x, times our du, which is 1 dx. And so now cleaning things up, we get negative 1/2 x squared cosine 2x. Let's write this as plus 1/2 x sine of 2x. Okay, from this new integral we could factor out the 1/2. So minus 1/2, and then we have the integral of the sine of 2x with respect to x. And now we can finish this off, because look at the new integral, compare it to the previous one after the first application of the integration by parts formula, and that x that was stopping us from fitting a basic form has vanished, and the sine of 2x is readily integrable. So these first two terms just need to be recopied. They are part of the solution. And we have the minus 1/2, and integrating sine of 2x, that would be minus 1/2 cosine 2x, and then we add our constant of integration at that point. So just finishing this off, minus 1/2 recopy x squared cosine 2x plus the 1/2 x sine of 2x, and now finally minus, nope, looks like plus, double negative, 1/4 cosine 2x, and then plus our constant. Okay, so at that point we'll look at another example, and in the second example we see x cubed e to the 2x. So again, what's stopping us from fitting the basic integration formula is, if this were going to fit a basic formula, it would be e to the u, because the exponentials dominate over the algebraics, and our u would be chosen to be 2x. The du is 2 dx. You can modify by the 2, and the problem is we only need dx to satisfy the du, and we have way more than that. We have x cubed. So integration by parts would be required, because again it's the product of two different classes of functions that does not fit a basic integration formula. So we would pick our u, x cubed, and our dv e to the 2x. With that, we associate the dx. Oh, I forgot to argue. The x cubed is algebraic, and the e to the 2x is exponential. So according to lie 8, the algebraic is our u. Okay, so then we calculate our du. It's 3x squared dx. Again, we don't modify it. We integrate dv to get v, and integrating e to the 2x. That's the formula for the integral of e to the kx. Again, I'll just flash it real quick. Here it is from before. 1 over k, e to the kx. So we get 1/2 e to the 2x. Okay, we don't add a constant there. We wait until we evaluate the final integral. But here's the integration by parts formula, a little trick. U times v, the product of the diagonal, minus the integral of v du. And that gives us u, which is x cubed, times v, 1/2 e to the 2x, and then minus the integral of v, 1/2 e to the 2x, times our du, which was 3x squared dx. Okay, so we'll take a step and clean this up. We get 1/2 x cubed e to the 2x, and then we have the minus, and from the new integral we could factor out this negative 1/2, I'm sorry, positive 1/2, as well as the 3. So we factor out 3/2, and then we have the integral of, okay, in terms of the order we prefer to put this in, e to the 2x times x squared e to the 2x is preferred. Alright, now notice what happened here, and you might be getting the idea about these powers of x. We started with x cubed that was bothering us. One application of integration by parts brought it down to x squared. So you can imagine now that if we do it again, another application of integration by parts, that is, this will be depressed down to an x, and then finally a third time it will vanish. So we're going to continue with integration by parts by choosing u to be x squared, dv equals e to the 2x dx in this new integral, because again the x squared is algebraic, it is exponential. So we get the du is 2x dx. We don't modify again. V is equal to integrating e to the 2x, 1/2 e to the 2x. The integration by parts formula again, u times v minus the integral of v du. Okay, this 1/2 x cubed e to the 2x is part of the solution. Just going to have to recopy that as we go. And then we have minus 3/2, and here's something important. I'm about to separate this into, I'm about to apply the integration by parts formula to this integral, which creates two terms, the uv and the integral of v du. And so therefore, I have to include parentheses or brackets, or I guess it would be kind of tricky to mentally distribute, so that's why I'm going to include brackets, this negative 3/2. So then applying the integration by parts formula to this new integral, we get u, which is x squared, v 1/2 e to the 2x, and then minus the integral of v 1/2 e to the 2x times our du, which is 2x dx. And so at that point, let's clean things up. We have 1/2 x cubed e to the 2x minus this 3/2 needs to be distributed. So times the first term, we multiply it by the 1/2, we get 3/4. And then we have x squared e to the 2x. Okay, now here's where you have to be careful. Distributing times the negative. Fortunately, this 1/2 cancels with the 2, so that makes 1. So we just have to worry about the negative 3/2 times this negative. So that would be positive 3/2. And then we're left with the integral of, okay, what's left over here is e to the 2x and x, which again we prefer to write as x e to the 2x. And then finally, one more application of the integration by parts formula. Algebraic exponential, algebraics are u. So u is x, dv e to the 2x dx again. Our du is 1 dx and our v 1/2 e to the 2x. And then the integration by parts formula, u times v minus the integral of v du, our little trick, gives us, okay, recopy 1/2 x cubed e to the 2x. Also recopy the negative 3/4 x squared e to the 2x. And then we have this plus 3/2. And again, I'm going to need brackets, parentheses, because that 3/2 is going to be distributed to the two terms created by the integration by parts formula here, which are ux times v 1/2 e to the 2x minus the integral of v 1/2 e to the 2x times the du, which is just 1 dx. Okay, so continuing, got 1/2 x cubed e to the 2x, the negative 3/4 x squared e to the 2x. This 3/2 again needs to be distributed. So times the 1/2 gives plus 3/4 x e to the 2x. And distributed to this integral, well, we have the negative, and we also have this 1/2 that needs to be multiplied by that 3/2. So it looks like negative 3/4. And then the integral of e to the 2x with respect to x. And finally, we are to a point where the new integral is readily integrable. And so we can integrate that. Recopy the 1/2 x cubed e to the 2x, the negative 3/4 x squared e to the 2x. This third term, the plus 3/4 x e to the 2x, is also part of the solution. And now finally minus 3/4 and integrating e to the 2x again, we get 1/2 e to the 2x. And now finally we could add our constant of integration. And so our final answer, 1/2, recopy everything here. And the minus 3/2 times 1/2 is minus 3/8 e to the 2x, and then plus our constant. Alright, so you will be happy to know that there is an easier way, and that's what we call the tabular method. So if there is a product, well, let me say this first. On our next page of notes, it says the following functions are cyclic. You could say cyclic or cyclic with respect to differentiation and integration. And the three factors that are cyclic are e to the kx, sine of kx and cosine of kx. They're cyclic with respect to repeated differentiations or integrations. That is, differentiate e to the kx and you get e to the kx back, times k, but we're not worried about constant multiples. Or integrate it and you get e back. Sine or cosine take two differentiations or two integrations to come back, but they're just modified by constants. Derivative of sine is cosine, kx times k, again the k is not an issue. And then cosine goes back to sine, modified by a negative and the k and such. But it takes two differentiations or integrations and they come back, so that's why we call them cyclic. And here's the comment. If there's a product of a cyclic factor and a polynomial, now it has to be a polynomial, but you'd be surprised at how many times we see this type of situation, we can use what we call the tabular method of integration by parts. So on the exam, I'm not going to tell you, hey, use the tabular method. You have to know. So you have to look for these cyclic functions and look for a polynomial. And that's exactly what we have here. X cubed is algebraic, but moreover, it's a polynomial because of the whole numbered exponent. Sine of 3x is trigonometric, but now we're referring to this as a cyclic factor. And once you have that case, then you know you can use the tabular method. And we modify our approach a little bit. Instead of saying u is equal and dv is equal to, we have a column labeled u. For some reason I always underline it twice. And a column labeled dv. And we're still going to be consistent with y8 in terms of our choice of u. And so that tells us to pick u to be the algebraic, x cubed. And the dv then is what's left, and that's the sine of 3x. Now, typically, we associate the differential dx with our choice of dv. But with this tabular method, the idea is that we're going to perform multiple differentiations and multiple integrations here. So we're not going to include the dx in the integrations. We just have to realize that the u column gets differentiated and the dv column gets integrated. And the beauty of this method is the fact that if u is a polynomial, you will be able to differentiate it successively and ultimately come up with 0. So that's the plan. So we're going to differentiate x cubed. If we differentiate it once, we get 3x squared. Twice we get 6x. Thrice we get 6. And then one more time we get 0. And then integrate dv the same number of times. And just make sure you line up your rows neatly. Okay, so you integrate it the same number of times. Now, every time we integrate sine or cosine, we get modification by 1/3. Sine it, and here's where you have to be careful of your signs, S-I-G-N-S. Sine integrates to be negative cosine, and the factor of 1/3, so negative 1/3 cosine 3x. Okay, next time cosine integrates to be positive sine, another factor of 1/3 makes it negative 1/9 sine of 3x. Sine integrates to be negative cosine, another factor of 1/3, double negative makes positive, 1 over 1/3 times 1/9, 1/27 cosine 3x. And then finally integrating cosine, we get positive sine, another factor of 1/3, 1 over 81 sine of 3x. And now all of the integration and differentiation, all those multiple applications of the integration by parts formula have been accomplished within the context of this table. And all we need to do now is take the product of the first entry in the u and the second entry in the DV, and then each subsequent parallel diagonal, and then the product of the horizontal, and we alternate signs. And the reason why we alternate signs is because of the repeated application of the integration by parts formula. First term is always positive. And this is when we're talking about taking the product of these diagonal terms. Negative, positive, negative. And then for the final entry, for the final product of the diagonal, we should say plus the integral of. But because this final entry is a 0, what we do is we think about what does it mean to take the integral of 0 with respect to x. That is, we probably don't think about that very often. And the fact is that if you think about this as anti-differentiation, that is, what is a function whose derivative is always 0, that would just be some constant of integration. And so therefore, if and only if the final entry in the U column is a 0, we can call that diagonal, the integral of the, horizontal, the integral of the horizontal product, we can call that our constant of integration. Okay? But that's only if the final entry in the U column is a 0. And then all of our calculus, everything's done. All we need to do is take the product of those diagonals, account for the signs. So first diagonal positive, x cubed, negative 1/3, cosine 3x, next diagonal negative, 3x squared, negative 1/9, sine of 3x, next diagonal here, positive 6x, 1/27, cosine 3x, next diagonal negative 6, 180/81, sine of 3x, and then the horizontal product should be the integral of, but it's the integral of 0, and as we just argued, that can be considered to just simply be the constant of integration. So then cleaning this up, minus 1/3 x cubed cosine 3x. See, let's reduce here. Double negative makes positive. 1/3 x squared sine of 3x. 6 and 27 reduced to 2/3. 2/9, excuse me. And there's positive x cosine 3x. And 6/81 reduces to 2/27, negative sine of 3x, and then plus our constant. Alright, so if you can imagine doing that the long way, it'd be very tedious. Okay, so obviously you want to use the tabular method for these situations, and the first page of examples was just to show you the long way, but this is the approach you'd like to use. Because that would have took 3 applications of the formal integration by parts formula to get down to a point where you could integrate the final integral. One thing to note about this is how, as you move from left to right, the powers of x decrease in the terms. Notice how this is x cubed, x squared, x to the first, and then the x to the 0, basically it vanishes. And also how the trigonometric functions alternate. That is, cosine, sine, cosine, sine. So that's a little double check when you do these problems. And there's nothing you can say about the coefficients and their signs or anything. You can't really follow any patterns there. But if you don't see that x cubed pattern, the decrease in powers pattern, and the alternation of signs, alternations of the trig functions pattern, you know you did something wrong. Okay, so final example, and again you have to know to use the tabular method, and it's when you have a product of algebraic, But moreover, a polynomial, again, a polynomial is a whole numbered exponent. And here we have an exponential that's of the form e to the kx. So that is what we are referring to as a cyclic factor. So we set up for the tabular method. Okay, we have two columns, one labeled u, one labeled dv. According to Lie again, algebraic is our choice of u. And that's always going to be the case in this situation, because if you consider Lie and you consider the fact that these cyclic factors are exponentials or trigs, and we're talking about a cyclic and a polynomial, which is the algebraic factor, the algebraic is always going to be your choice of u, because they precede the trig and exponential in our hierarchy. So your u is always going to be the polynomial, next to the fourth in this case. dv is what's left, that's e to the 3x, but again, we do not associate the dx. That's because all the integrations and differentiations are going to take place in this table. And the idea is that because u is a polynomial, you'll be able to differentiate it to get 0. So once 4x cubed, twice 12x squared, 3 times 24x, 4 times 24, and finally we get a 0. Just make sure you line up your rows neatly, and every time we integrate e to the 3x, we get a modifying factor of 1/3. So 1/3 e to the 3x, another factor of 1/3, 1/9 e to the 3x, another factor of 1/3, 1/27, e to the 3x, another 1/3, 1/81, e to the 3x, and finally another factor of 1/3, 1/243, e to the 3x. And then all of the calculus is finished. We just take the product of the first entry in the u, second entry in the dv. That's our first diagonal product. And then all of the subsequent parallel diagonals, product of the horizontals. We alternate signs, always starting positive, so positive, negative, positive, negative, positive. And then I suppose this would be minus the integral of 0, but it doesn't matter, minus c plus c, just call it plus c. Because again, if and only if that final entry in the u column is a 0, can we call that horizontal product a constant of integration? And that's because, as we argued earlier, the 0 is a constant in general. So everything's done. Just take the product of these diagonals, account for their signs. I'll show it literally. You can skip steps if you like. So we have first diagonal product x to the 4th, 1/3 e to the 3x. Next diagonal negative 4x cubed. And then 1/9 e to the 3x. Next diagonal product positive 12x squared. 1/27 e to the 3x. Next diagonal product negative 24x. 1/81 e to the 3x. Final diagonal product positive 24 and 1/243 e to the 3x. And then the horizontal should be the integral of, but as we've argued, plus c. Alright, and just make it look a little prettier. 1/3 x to the 4th e to the 3x minus 4/9 x cubed e to the 3x let's see, 3 goes into 12 4 times, and into 27 9 times. X squared e to the 3x. Negative 3 is a factor here as well. That'd be 8 over 27. X e to the 3x. And then finally plus, again, 3 is a factor. Goes into 24 8 times, into 243 81 times. E to the 3x, and then plus or constant. And here you can notice something in terms of a pattern as well. The fact that, well, e to the 3x is a common factor of every term. And you can factor it out if you want, but I'm not concerned about that. But do notice the pattern of the decrease in powers on the x variable as you move from term to term. That is, here we have x to the 4th, then x cubed, x squared, x to the 1st, essentially x to the 0, which is 1, so the x vanishes. Okay, so that's the end of that. We got 2 more topics left, and then that'll be the end of the material for the second exam. So we'll see you when you're ready for topics 8 and 9.